Okay, please turn the page over to page 14 and we'll get started on the next video. So last time we talked about shear stress, and now we're going to talk about the second term in that equation, viscosity, or mu. Now viscosity is a fluid property, kind of like density is a fluid property, and you're going to find it in your appendix in the back of your textbook. The official definition of viscosity, it's basically is defined by that equation, tau equals mu du dy. So basically how much force or stress do you need to apply to get that fluid to move. Its symbol is mu. Looks kind of like a U, but with a little thingamabob at the front of it. That's actually a Greek mu. Okay, and you'll see those units when you look it up in the back of the book. Think of viscosity as kind of the thickness. So for instance, if you have a milkshake and then you have a cup of water, if you put a straw in the milkshake, it's going to take a certain amount of force to get that shake to flow. Now if you put the straw in the water, it's not going to take nearly as much shear stress to get that water to flow, and that's because the water has a much lower viscosity than the milkshake does. So high viscosity fluids are things like honey, tar, corn syrup. Low viscosity would be something like air or any of your gases. Somewhere in the middle would be water, for instance. So viscosity is a property of the fluid, but it is also a function of temperature. So sometimes in the back of the book you're going to see the table is going to have temperatures in it, and your viscosity is going to be varying with temperature. So Newton came up with tau equals mu du dy and the idea of viscosity. So therefore fluids that have constant mu's, in other words mu's or viscosities that don't change with shear stress, those are called Newtonian fluids. And they're not all Newtonian, but air and water are Newtonian fluids. If it is something that does change with shear stress, and there are examples, for instance, quicksand, paint, toothpaste, ketchup, those are all non-Newtonian fluids. Blood, when blood is moving very slowly under small shear stresses, it'll be much thicker than when it's exposed to high shear stresses. So the ones that we're going to deal with mainly in this class are going to be Newtonian. Okay, so something else that's associated with viscosity is something called the no-slip condition, and this is very important in fluid mechanics. And basically what it is at a surface, the velocity infinitesimally close to that surface, right next to the surface, the velocity of the fluid has to be the same as the velocity of the surface. So V fluid equals V surface, right at that surface. So in our equation where y equals 0, if y is at the wall, then the fluid has to be moving the same velocity as that surface. That's the no-slip condition, very important. And an example of the no-slip condition, if you turn the page. So let's say we have a bus that's moving into the still air. Well, instead of looking at it as the bus moving into the still air, let's instead look at it as if the air is flowing over the bus, like the bus is in a wind tunnel. It's the same thing, it's just easier to think of. So what happens is out in front of the bus, we have a constant uniform incoming velocity, right? But as we get to the surface of the bus here, so as that air flows over the bus, when it hits the bus, right here at the bus's surface, the velocity is going to have to be 0 if it's just a still bus and the air is moving over it, right? The velocity at the bus has to be the same as the bus itself. Okay, out here further, away from the bus, it's eventually going to be back to that u infinity. Okay, and maybe a little closer even to the bus, it's still u infinity. that's where the bus is not affecting the flow. Okay, but between there and the bus itself, the velocity is going to be changing, and we can draw a velocity profile, maybe something like that, where here are our velocity vectors. It's 0 at the surface of the bus, and eventually it goes out to u infinity, and the velocity is not changing anymore as you go far away from the bus. Okay, so this no-slip condition is due to viscosity, and it is going to affect and give us velocity profiles, for instance, on the top of this bus. This area here, where the velocity is actually changing, that has a particular name. That is called the boundary layer, and it's very important in the study of fluid mechanics. And it's basically the area boundary layer where you have a du dy. Okay, the velocity is changing in the y direction. Alright, so stop here and do quiz questions 3 through 5, and then I'll see you on the next page in the next video.